Okay, before we begin, are there any questions? Let me mention before I share my screen that I've done some grading. Let me call up the grading book, then I'll have an easier time talking about it. But I got some labs graded. One of them I got graded last weekend and one last night. And a few other things graded. With the labs, remember, on the first grading, you can, if you didn't get a perfect score, meaning a 5, you can turn in the lab again for full credit a second time. Yeah, let me see what labs those are. Almost there. So lab 1 and lab 2 have been graded for the first time. And this Saturday, if you didn't get 100%, you can turn it in again for full credit. You must turn it in by this Saturday because that's the deadline for, boy, this isn't working right. October 14th for turning it in the second time. You may turn it in late, in which case you'll get a late penalty. But if you turn it in late, you have to email it to me. Any questions about any of that? Boy, I'm still not getting this to show right. Yeah, that's better. All right, let me close the grade book and then I'll share my screen. Should be seeing my screen now. So today is October 12th, and we're supposed to be, let me scroll up a little bit, talking about chapter 3, observing microorganisms. There is a lab today, and we'll talk about lab 4, covering stains. The lab will be at the normal lab time. Any question about what we're doing? I guess I should mention yesterday you should have taken quiz 1, covering chapters 1, 10, the start of chapter 2 in labs 0, 1, and 2. If you have not taken it, let me know. It is possible to take it late by, well, anytime on Friday, up to about midnight on Friday. On Saturday, the answers will be showing, in which case I will no longer allow you to take the quiz. Any question about any of that? All
Do
right.
we have to be in the lockdown browser in order to view the answers for the quiz?
Yes, the answers
Okay,
aren't showing yet, but
right. Okay.
you should be able to see the answers with Lockdown Browser. And I don't have Lockdown Browser, so I've never seen the answers. But if you have trouble, just let me know. You might also contact the computer help desk to ask, how do I see the answers on my quiz, which is in Lockdown Browser. But you cannot see the answers without Lockdown Browser because you can't get into the quiz without Lockdown Browser. And it's Respondus Lockdown Browser, by the way. All right. Let me scroll that up. Can't get it up. There it is. All right. If there's no further questions, let me go ahead and go to the top here. And let's go to chapter 3. I probably better check chapter 2 to make sure we finished it. I think we did. Yeah. We did finish chapter 2. All right, so let's begin chapter 3. I can close chapter 2 down. All right, chapter 3, observing microorganisms. The major goals and rough outline are shown in this slide. Know the terms, what's resolution, refraction, what are stains, what's a basic and acidic dye, what's a smear preparation, what's a mordant, what is peptidoglycan. 2, understand the sizes of organism and the properties of microscopes. Understand the major differences between the light microscope and the electron microscope. And then 3, understand why staining improves resolution. 3A, know the 3 types of stains. There are simple stains, differential stains, and special stains. And then 3B, understand the Gram stain, its procedure, and the basis of its differential staining. Any questions about what we're going to cover? All right, observing microorganisms. We use in science the metric system. It's also used in medicine. The metric system is actually an easier measuring system because everything is based on a unit of 10. Let me blow this up. So the basic unit for length is the meter. 1,000 meters is 1 kilometer. You don't need to know 1/10 of a meter, the decimeter, but you should know 1/100th of a meter is a centimeter, 1,000th of a meter is a millimeter, and that's the smallest unit we have on a ruler that has the metric side. So that would be the smallest marking on a ruler. Then there's a micrometer. That is the size of cells under the microscope, the light microscope. A nanometer, a micrometer is 1 over a millionth of a meter, or 1 times 10 to the negative 6 meters. The nanometer is the size of things you see under the electron microscope, and that's 1 over a billion, or 1 times 10 to the negative 9th meters. And then you don't really need to know a picometer, but that's 1 times 10 to the 12th, negative 12 meters. And so to convert from meters to like millimeters, for example, you just multiply by 1,000 to get your number of millimeters. Any question about that? All right, you are expected to know the metric system, and you'll be quizzed on, well, most of this table here on the left. Like I said, you don't need to know the decimeter or the picometer, but you should know all the others. Converting from one to another. And generally, if you just remember everything based on the meter, then you can switch to a millimeter. And frequently, like when I'm converting, I don't know, centimeters to micrometers, I will frequently convert a centimeter to a meter and then the meter to the micrometer. That's a little longer because it's 2 steps, but if you don't remember the number of micrometers and a centimeter, that's just an easy way to do it. The metric units are good. Also, that the meter is the basics for the length, but we have a volume, and that's going to be a liter. And then you use the same prefix, the kilo and the centi, for the liter. So there's a kiloliter, a centiliter, a milliliter, a microliter, and other units. In measuring, we usually use millimeter in medicine because that's, I don't know, what we inject into someone or take out their blood in milliliters. And then in gasoline, if you fill up your car, if you go to a country that uses metric, you get it in liters. And then there's the weight or the mass, and that's measured in grams. So that would be the basic unit. And once again, you use the prefix, the kilo, for kilograms. And I think people are weighed in kilograms. I'm sorry, I'm not using the metric system for getting my weight, so I don't know, but I believe that's true. And then you should know a centigram, a milligram. A microgram isn't used very much, but you probably should know that one too. And then they're all the same units, so that to convert from a gram to a milligram, it's 1/1000th. A milligram is 1/1000th of a gram. Any question about any of that? All right, you do not need to know the fourth column here. We're not going to convert metric units to English and English units to metric, so you do not need to know that. That is actually a difficult calculation, and I happen to know a few of them. Let me see, I used to know how many centimeters are in an inch, and I think it's 2.4, which probably isn't even in here. Oh, there it is there, 2.54, I think, for 1 inch. And I used to know kilometers to mile, something like 0.6, there it is, 0.62 kilometers equals 1 mile, or maybe it's 1 kilometer equals 0.16, 0.62 miles. Like I said, I don't remember that, but like I said, those are also complicated. You don't need to know that, but you should know to measure things in metric and then to convert things in metric. And there's two main reasons for learning metric, and that is science uses metric, and so does medicine. And then this is the other reason why you should learn the metric system. This map is showing you all the countries in the world that do not use the metric system. And as you can see, there's only 3 countries in the world that don't use the metric system. And 2 of these 3 are actually slowly converting to using the metric system. The United States is one of them that is slowly converting to using the metric system. And actually, it was President Jefferson who passed through Congress the, I don't know, the law, whatever you call it, for converting the United States to using the metric system. And as you can see, in the United States, we are very, very slowly converting to using the metric system. It is true our rulers have metric units on it. And nowadays, it's very difficult to buy a car that's not showing you the speed limit or the speed you're driving at in both metric and English. And oftentimes the signs on the highway will tell you the speed limit in both metric and English. Any question about any of that? All the other countries in the world use the metric system. In the United States, the only big country that doesn't. All right, some typical sizes of microorganisms. A eukaryotic cell, they're putting the range for 10 to 500 micrometers. If we're talking about the biggest cell you've ever seen, a chicken yolk, which is a cell, the yolk of a chicken egg, it's bigger than 500 micrometers. And I'm not sure what the smallest size of a eukaryotic cell is. And then they're putting the size of the prokaryote cell from 1 micrometer to 10 micrometers. 10 is much larger than most prokaryotic cells. The average is 1 to 2 micrometers. And then the smallest prokaryote is about 0.4 micrometers in diameter. And that's, I should mention, that's the smallest viable prokaryotic cell. There are some smaller, but people think that they're not viable. Any question about any of that? For viruses, just to compare, and I guess I should mention that prokaryotes are about 1/10 the size, just a rule of thumb, 1/10 the size of a eukaryote cell. And then viruses are about 1/10 the size of a prokaryote cell. This is showing you the size of viruses, which this is about right. The smallest viruses is down to about 20 nanometers, that's 0.02 micrometers. And then the largest virus is about 0.44 micrometers. And that means the largest virus actually is the size of the smallest prokaryote cell. And we'll talk a little bit more about that when we're talking about viruses late in the term. And that's the diameter of a virus. If you take the length of a virus, the longest virus, Ebola is one of the longest virus, is actually 1 micrometer. And that length is approaching the size of a prokaryote cell. But the Ebola virus is not the largest virus, at least in the diameter, because it's long and skinny. Any question about any of that? All right. So I think we've seen this before. If not, we'll see it one more time. This is showing you the size of things, how you can see with your eye, the light microscope and the electron microscope. And we can see, obviously, big objects like people and the chicken egg, which, remember, the yolk is the largest cell that you guys have ever seen. The largest cell currently on the planet is the yolk of an ostrich egg. However, not many people have seen that. I've never seen that, not even on television. I have seen on television the yolk of a turkey egg, and I once had a student who said that they saw the yolk of a turkey egg, but most of us have never seen the yolk of a turkey egg. So the largest we've seen is the yolk of a chicken egg, largest cell. And then about the smallest cell that you guys have seen is a frog egg, assuming you've seen a frog egg. There actually is a cell a little bit smaller that you might have seen, and that is when you cut into a watermelon. Let me end the show here and bring up paint. So the watermelon is like this, and then it has the different areas with the seeds over here. Yeah, I guess that should be a little more centered there, there. Probably there's more than 4, but I don't know. Anyways, this region here in the center, which has a shape somewhat like that. If you ever cut the watermelon and you see a little shape in this region here, and it's a cell like a 6-sided or 8-sided cell. It's very microscopic, so you have to look very hard, but you actually can see the cell of the watermelon. It is a very large cell that our human eyes can actually see. And for us, most of the time, it's going to look like, well, maybe a little bigger than that. Let's see if I can get that a little bigger. Most of the time, it'll look a little bigger than that. Maybe like that. Cells under that size have to be seen with the light microscope. That includes most eukaryotic cells, all prokaryotic cells, and then most viruses cannot be seen with the light microscope. To see most viruses, you need the electron microscope. The electron microscope can also see things smaller than a virus, and that would be mainly large proteins. They're smaller than a virus. And then small molecules are smaller than a large molecule, like a protein. And water would be an example of a small molecule, which that's actually water shown right there. And then atoms are smaller than a small molecule. So these are the things, the main things you need to know about. And you don't need to know their size exactly, but it's probably a good idea to know that a small molecule in proteins and viruses have to be seen with an electron microscope, prokaryotic cells and most eukaryotic cells with a light microscope, and then chicken eggs and people, obviously you can see with your unaided eye. This chart is telling you the size of things, but realize that the author has a mistake here. It has 1 micrometer there and 1 micrometer there, and I put a correction in there. That should be 1 millimeter right here. Any questions about any of that? So mainly what you need to know here is just the relative sizes of things. A person is larger than a chicken egg, larger than a frog egg, larger than a eukaryote, most eukaryotic cells, larger than prokaryotic cells, larger than viruses, etc. All right, let's talk a little bit more about the light microscope. In the lab, if you were to go into our lab, we have compound light microscopes. A compound light microscope is one that uses light. That's why it's called light microscope. And it's compound because it has 2 lenses that magnify. It has an ocular lens and an objective lens, and both of those lenses magnify the size of the image that we're seeing. The total magnification is the magnification of the objective lens times the magnification of the ocular lens. Most microscopes have objective lenses of 4x, 10x, 40x, and 100x for their objective lenses. And generally, I call the objective lenses the 4x lens, the 10x lens, the 40x lens, and the 100x lens. However, they do have different names, which confuse a lot of students. The 4x lens is called the scanning objective lens. The 10x lens is called the low power lens, and students often get the 10x confused with the 4x when they use the term low power. So it's a bad choice to use it if it confuses you. The 40x lens is called the high power lens, and that gets students confused because when they call it the high power, they get it confused with the 100x, and the 40x is not the 100x. It's the high power lens. And like I said, I just don't like that term because it's not the highest. The 100x lens is the highest, and it is called the oil immersion objective lens. Any question about any of that? All right, so most microscopes have an ocular lens that magnifies 10 times. And all of our microscopes in the lab have an ocular lens that magnify 10-fold. So that means the 4x lens, its total magnification will be 40x, because it's 4x times 10, which is 40x. And then the 10x lens will be 100x, because it's 10x times 10 is 100x. You see how we obtain the total magnification? Anyone not see that? All right. You should know the parts of the microscope shown here: the ocular lens, the body tube, or the arm of the microscope, which you use the arm as well as put your hand under the base for carrying the microscope. The objective lenses here, you should know that. The stage, the condenser, let me blow this up. And this one has the iris diaphragm below the condenser. If you remember in the lab we had last time, the iris diaphragm was above the condenser. And what these two do is they put a cone of light from the lamp through this slide where your specimen is. And the iris diaphragm can close that cone of light or open it. And then the condenser, all it does is it focuses the light into a cone. It is not a magnification lens. The diaphragm acts like a shutter on a camera, closing and opening. And we'll talk a little bit more about that. The illuminator, also called the light or the lamp, is what gives the light for the microscope, the light microscope. And then we have the large knob here, which is the coarse focusing knob, the small knob, the fine focusing knob, and there's the light switch for turning on and off the light. And I think that's a rheostat built in, because I don't see a second one. And that means that if you turn it all the way off, it'll click and it'll turn the lamp off. And then you can turn it on and then rotate it to increase the amount of light coming through the lamp. Any question about any of that? All right. This is a simple microscope. It is a light microscope. Although this one doesn't have a light source, you have to hold it up to a light source. And it was actually one made by Antony van Leeuwenhoek. Why it kind of looks a little bit primitive, because it was one of the early microscopes. It's a simple microscope because it only has one magnification lens right there. A simple microscope really is nothing other than a super duper magnifying lens, because it only has one lens for magnifying. Any question about any of that? And if you want to know how this worked, Antony stuck what he was observing on the pen and then took the light microscope and then held it up to the sun or to a light source and then viewed the specimen. All right, when discussing microscopes, you should know the term resolution. That is the ability of a lens to distinguish 2 points as 2 separate points. So when you have 2 points close together, as long as you can distinguish them, then you have resolution. If, however, they're so close together, you cannot distinguish them as 2 separate points, you do not have resolution of those 2 points. With the light microscope, the highest resolving power we can get is 0.2 micrometers. So the best we can distinguish 2 points is they have to be at least 0.2 micrometers away from each other. Otherwise, when we look at them under the light microscope, you will not be able to distinguish them as two separate independent points. The resolving power of the light microscope is determined by the resolution limit of white light, and it has something to do with the wavelength of light. And I'm not going to tell you exactly, because you can look that up in one of the it's one of the questions, either in the lab or in the worksheet for the lecture. I don't remember which, but there is a question about what is the resolution limit for white light and why. And like I said, the resolution limit is 0.2 micrometers, and we can't resolve anything closer than 0.2 micrometers apart from each other as two distinct points because of the resolution limit of white light. With the best light microscopes we can build, they have an ocular lens which is 20x, and that means the total magnification is 2,000 times. If you ever were to get a lens that would allow you to magnify more than 2,000 times, it's empty magnification, because 2,000 times is the limit of the resolution of the microscope. Meaning, even if you were to magnify, let's say, 3,000 times, you would not be able to distinguish 2 points from each other that are closer than 0.2 micrometers. So that's why I mean the magnification will be empty. Any question about any of that? The best microscopes that have ever been built can magnify 2,000 times. Remember that our microscopes in our microbiology lab can only magnify 1,000 times. And it's because they have a 10x ocular lens, which is just less expensive than the 20x lens. Any question about any of that? All right. So when we're looking at this under the microscope, we see this. And these 2 points are 0.2 micrometers apart from each other, which is 200 nanometers. And we can distinguish these two as two separate points under the light microscope. However, all of these points, and probably that one too, you cannot distinguish as separate points because their distance is less than 200 nanometers or 0.2 micrometers. 200 nanometers is 0.2 micrometers. Any question about that? So that would be how these will look under the microscope because of the resolution of the microscope. And then these two, even though they're blurry, the resolution does allow you to distinguish that as a separate point from that one. Any question about that? Another property you need to know with the microscope is that light can refract. The refractive index is the light bending ability of a medium. Whenever light passes from one medium to another, the light will bend, and that we call refraction. And that's why it looks like the pencil is bent right there, or right there in the artist's rendition. And that's because when the light comes out of the water and enters the air, the light will bend, making it look like the pencil is bending. Any question about that? Whenever light is only going through one media, like if it's only going through the air, you do not have the bending of light, which we call the refraction of light. This only happens when light moves from one media to another. And actually, I suppose we have light, 3 medias here. We have light going through the glass, light going through the water, and light going through the air. So you do have three medias here. However, we're not really looking at the light going through the glass. Maybe that right there would be the light going through the glass. I'm not sure what that is. That could be just the reflection. The refraction of light is very important for life. For example, a bird that wants to catch the fish in the water, the bird will see the fish in this position, even though the fish is really in this position. And what's happening is the fish is in this position, and the light hitting the fish will go through the water, and then the light will be refracted at the surface of the water and the air, and that will make the fish appear to be in this position in the water. The bird knows that the fish is not in this position in the water, and when it tries to catch the fish, it will try and catch it down there. And this is all instinct for the bird, but my point is that life had to get used to the refraction of light, like when the bird's trying to catch this fish. It knows not to go for the fish here because that's where the fish looks like it is. The fish is really deeper down here. Any question about any of that? And that's because of the refraction of light. We use oil on the microscope to reduce or remove the refraction of light. So when we have a glass slide and then shine light through it, we will get the light refracting at the surface of the glass and the surface of the air. And that will mean that the light will be bent there. And as you can see, this light ray will be bent back into the slide, so that we will never even see. And this one will be bent hard enough so it will not go up into the objective lens. This one will be bent, but it will be collected by the objective lens. And then some light rays will not be refracted from the glass to the air and will go straight up into the objective lens. Any question about any of that? Everybody's good? Well, let me mention that this one is showing you there's a second refraction of light, and that is when the light is traveling from the air to the glass of the objective lens, the light can be refracted right here. So the light will be refracted right there as well. Oil has the same refractive index as glass. And so if we put oil in between the glass slide and the glass of the objective lens, then the light will not be refracted. So not only will we get this ray and this ray, we will also get this ray, which would be missing if we did not use the oil. And that ray we will not catch, but it actually will come out of the slide because there's no refraction. Any question about any of that? So this explains why the refraction of light decreases the resolution when we do not use oil. And that is some of the light is refracted and cannot be collected by the objective lens, decreasing the resolution of the microscope. And then if we use oil, we can collect that light, that ray, and that will improve the resolution when you use oil, because you'll collect more light than without using oil. Any question about any of that? So we use oil to keep light from bending or refracting, and that will improve the resolution and clarity of the image seen under the microscope. All right, let me briefly mention that with the oil immersion lens, you need to use oil. Otherwise, the lens does not magnify any better than the 40x lens. And there's no reason to use the 100x lens because the 40x lens is a better and easier lens to use. But with the oil immersion lens, you need to use oil. Any question about any of that? And then I guess I should mention, whenever you use oil in the microscope, you must remove it with lens paper. All right, bright field illumination is what most compound light microscopes use. In bright field illumination, we have a light source which shines rays onto the specimen, which are then collected by the objective lens to form the image. It's not showing you where the image is. Anyways, the bright field illumination is used by the microscopes in our lab. Bright field illumination differs from dark field illumination in that the object's background is very bright. It just looks like white, and that's because the light goes right through the glass slide, and that's the background of the slide. The object also looks light, although the object is stained, so it will be colored. Not the object, the specimen, sorry. In dark field illumination, let me blow this up. Let me see if I can do it from here. In dark field illumination, we do have a light source, but there is a disk that blocks any direct rays coming from the lamp, going through the specimen, and then being collected by the objective lens. So any light rays directly coming from the lamp are blocked. And that means that the background of the slide will be totally black because no light is coming from the lamp, going through the slide, and then being collected by the objective lens. That's why the background is dark, and that's why it's light here, because this doesn't have that disc in there. The specimen does look lighter, but it is darker than this specimen. What's happening is some light comes at an extreme angle from the lamp and can pass through the specimen, and the light will be bent by the specimen such that the light ray will be bent hard enough that it'll actually be collected by the objective lens. So the only light we get is light coming through the specimen, which is then bent into the direction of the objective lens. And that's why the specimen is showing up fairly light compared to the background, but darker than the bright field specimen. Any question about any of that? So you do need to know about bright field illumination because that's what a regular compound light microscopes use. You should know what dark field illumination is. You do not need to explain exactly what it is, but you need to know what it is and that the background of the cell looks dark and the cell itself looks lighter than the background, just not as light as the bright field cell. Any question about any of that? All right. This is an electron microscope, and it has several differences from the compound microscope. One, it's obviously much bigger, and two, instead of using light, it uses electrons. It uses a beam of electrons to observe the specimen. How the beam is focused is not using glass lenses. It uses electromagnetic lenses to bend the beam of electrons. Electrons have a negative charge, so if you have an electromagnetic lens, you can bend the electron. Electrons have a shorter wavelength than light particles. I used to know what that was called, a photon. And that means they can be magnified further than light can be magnified, and this gives greater resolution. This allows the examination of viruses in internal cell structures too small to be seen under the light microscope, such as this and this. These cells are being viewed by an electron microscope. There are two main types of electron microscope. There's at least 4 types of electron microscope, but there's 2 main types, and we do expect you to know the 2 main types. There's a transmission electron microscope and a scanning electron microscope. And let me blow this up. What do you notice that looks different between this specimen and that specimen? How does the transmission electron microscope differ from the scanning electron microscope? Anyone? How do they look different?
Well, is that the inside? You can see the inside of the cell? Is that
On the
what it is?
transmission electron microscope, you can see the inside of the cell. On the scanning electron microscope, you cannot. What are you seeing on the scanning electron microscope? Come on, there it is. What are we seeing here? It's not the inside of the cell. It's the, come on. It's the outside of the cell, people. So you can only see the surface of the cell on the scanning electron microscope. And then there's another difference here. Anyone notice it? How does that object look? How does that object look? Anyone? All right, I'll ask you this question. Is this object in 2 dimensions or in 3 dimensions?
3.
This one's in 3 dimensions, so you can see X, Y, and Z axis on this one. What's above this? I don't know, this little dot there. What's below this little dot there? All right, on this one here, can you see this one in 2 dimensions or in 3 dimensions? You guys aren't willing to cooperate. Anyways, that's the main difference between the transmission electron microscope and the scanning electron microscope. The transmission electron microscope only sees a plane, and you can see inside the cell. If you were looking at the exact top of the cell, like if we were to scan right here, you could see the very top, but once again, you only see the plane. So this one only sees one plane of the cell. This is the scanning electron microscope, and it sees the surface of the cell. It cannot see inside the cell. Okay. And then one is in 2 dimensions, the other is in 3 dimensions. Here we're looking at a scanning electron microscope. You can see the object in 3 dimensions. And here's the transmission electron microscope. It's in 2 dimensions, and I'm trying to remember what else I'm supposed to say here. This is the membrane of a chloroplast. Another type of electron microscope that you do not need to know, I'm just mentioning it because we're not going to be tested on it, is the scanning tunneling microscope. It uses a metal probe to scan a specimen, and it has very low resolution. You can see 1/100th of an atom, so even less than an atom. The fourth type of electron microscope is the atomic force microscopy. Uses a metal and diamond probe inserted into the specimen and produces 3D images of the specimen. All right. When we look at a specimen under a light microscope, we normally stain them. Which cells here, the ones on the left or the ones on the right, are easier to see?
On the right.
On the right. And that's the only difference is the cells on the right are stained. Staining, all it does is increase the contrast between the cell and its background, which is usually the glass of the slide. And here we can see that the cell is there, but has very little contrast to the background of the slide. So it's very hard to view the cell there. Whereas when we stain them, they have a very intense contrast between the background of the slide and the cell. And that is all staining does, increasing the contrast between the cell and the background of the slide. Most microbes are colorless and therefore have little contrast with the slide or the medium that they're in. To see them, at least to see them well, we need to stain them. Staining is all it is coloring the specimen or the background to increase the visibility and increase the contrast of the specimen with its background. A smear is something that's made on a slide, and usually it's a bacterial smear where you put the bacteria in a thin film so the microbes will be on the slide in a thin film. When we're making a smear, we do not do any staining, have no staining reagents, no even washing steps in making a smear. It's something we do prior to doing the stain. And usually after the bacterial smear is made, we will fix the cells to the slide, we'll air dry them, and then heat fix them. And that's to get the cells to attach to the slide. The cells will attach to the slide if we allow them to air dry on the slide and then heat fix them to the slide. If you don't do that, and then you begin staining that bacterial smear, most of the cells will come off of the slide because the staining process itself is going to add a liquid, and that will begin washing the cells away unless they're attached to the glass by air drying and heat fixing. Any question about that? One other advantage to heat fixing the bacteria to the slide is that tends to kill many bacteria. And so usually when we have a bacterial smear and then we air dry it and then heat fix it, that usually kills most of the bacteria. Any bacteria that have endospores will not be killed by this procedure. But if they don't have endospores, most of the cells will be dead. Any question about any of that? All right, a stain is also called a dye, so those two words are used interchangeably. A stain, all it is a salt consisting of a positive and a negative ion. In the dye, it has two parts, the positive and negative ion, and one of the ions is colored. We call that the chromophore. A basic dye is where the chromophore is the cation, meaning the colored portion is on the positive charge of the molecule. An acidic dye is where the chromophore is on the negative charged part of the molecule, the negative ion. And that is called the anion. The positive ion is called the cation. Any questions about any of that? So some stains are basic dyes because the colored portion is on the positive part of the stain or the molecule that makes up the stain. And then some dyes are acidic dyes because the colored portion is the negative part of the dye or the negative part of the molecule which makes up the dye. Any question about any of that? Bacteria cells have a slightly negative charge. Therefore, a basic dye is better for staining the cell because the positive charged dye will attach to the negative charged cell. Some examples of a basic dye are crystal violet, methylene blue, malachite green, and safranin. And all of these we have talked about or we will talk about in the lecture and the lab. Today we'll talk about crystal violet and safranin. I think we talked maybe a little bit about malachite green. I don't remember if we do this in the lab or in the lecture, but we definitely will talk about crystal violet and safranin. Any questions about any of that? All right, an acidic dye typically stains the background of the cell and not the microbe. Remember, an acidic dye has a negative charge and the bacteria has a negative charge, so the acidic dye will be repulsed from the cell. It will not stain the cell, but the acidic dye stains the background. That's the glass of the slide. And that still allows you to have contrast between the cell and the background. Some examples of an acidic dye are eosin, acid fuchsin, and nigrosin. Acidic dyes stain the background instead of the cell. And because of that, we frequently call an acidic dye a negative stain. This term comes from old film, what do you call that? Camera work, where they had Polaroid film, and you would get with your printouts, besides the colored photograph, you would get a negative. And the negative is the reverse for what the photograph looks like, meaning anything that looks dark in the real photograph will look light in the negative, and anything that looks light in the real photograph will look dark in the negative. And that's why it was called a negative in the film. And we call it a negative staining because it's staining the background of the cell instead of the cell. Any question about any of that? But negative staining is just using an acidic dye. All right, here we see our two types of stains. A basic stain, where the cells are pinkish or pink purplish, and you can easily see the cells because there's big contrast between the cell and the background of the slide. Here is a negative stain where we're using an acidic dye, and it's staining the background of the slide and not the cells, but you still have a good contrast between the specimen, the cells, and the background of the slide. So either stain stains the slide well and increases the contrast between the cell and the background of the slide. Any question about any of that? This is a simple stain because we're only using one dye in each case. There are three main types of stains: the simple stain, the differential stain, and the special stain. A simple stain is a stain that contains only a single dye. Its primary purpose is just to increase the contrast between the specimen and the background of the slide. Oops. Let me end the show here and go back. So that increases the contrast between the cell and the background of the slide. The stain is usually applied to a fixed smear, a bacterial smear, for a certain length of time. It may be washed off, dried, and then examined. Remember, the bacterial smear is not something you do while you're staining the cells. The bacterial smear is something you do before you stain your cells. And then the staining of the cell is not making the bacterial smear. I'm trying to hammer that in because a lot of people get those two confused. All right, any question about any of that? So usually the stain is applied for a certain length of time. The stain is then removed, and it may be washed off, dried, and then examined under the microscope. A mordant is something we use to intensify the first stain. In this case, we're only talking about a primary stain, a simple stain. So all a mordant would do would be intensify the simple stain. The functions of a mordant is it does not function as a stain itself, but it increases the affinity between the stain and the specimen. It usually makes the cell a little more visible, makes it a little more darkly stained, because like I said, it's binding with the stain and then increasing its size, making it show up better. Increasing the contrast would be another way of saying it. Another mordant simply coats the specimen to enhance it, thereby making it easier to see and increasing it. An example of a mordant is when we're doing the flagella stain, we apply the mordant several times to put a layer down on the flagella, and each time you do it, apply the mordant, you get a different layer. And then eventually you'll be able to see the flagella. The flagella does not show up under normal microscope stains. Even the differential stain does not show up the flagella. It's too small of a cell structure. And so we have to do the flagella stain. And one of the steps it does is it applies a mordant, which then layers the flagella, making the flagella easier to see. Any questions about simple stain? If not, let's talk about differential stains. A differential stain is one that reacts differently with different kinds of microbes. So you can distinguish between two types of microbes because they will look different. Usually, a differential stain uses two or more dyes, but that is not required. The differential stain just has to show differences between two cell types. The most commonly used differential stains are the Gram stain and the acid-fast stain. The Gram stain is a differential stain developed by Hans Christian Gram. You don't need to know the year, in 1884. What he did was he used it to be a differential stain to determine if a patient had a bacterial infection. And what he was trying to differentiate was between the bacteria and the patient's own cells. When he was using the stain, the bacteria would stain dark purple, and then the patient's own cells would stain a lighter pink color. So it was differential the way he was using it. And microbiologists started using his stain, and then they realized that the Gram stain was a very useful stain in bacteriology because it could classify all bacteria into two very large groups, the Gram-positive cells and the Gram-negative cells. And here we're seeing Gram-positive cells stain a dark purple, and the Gram-negative cells stain a lighter pink color. The difference is the Gram stain is staining the cells based upon their cell wall. If the bacteria has a very thick layer of peptidoglycan, it will stain purple with the Gram stain. However, if the bacteria have a very thin layer of peptidoglycan in their cell wall, the bacteria will not stain purple, the bacteria will stain pinkish. And we'll talk about why a little bit later when I'm talking about the Gram stain. We're not going to have time to talk about the Gram stain, so let me just introduce the topic. The Gram stain is the main differential stain, and what you do to do the Gram stain is first you make a bacterial smear on a glass slide. You want the smear to be very thin, ideally only one layer thick, and that way the stain can easily get in the cell, or if we want to remove the stain, it can be easily washed out of the cell. If you have several layers of bacteria, it'll be harder to get the dye to go through the cells on top to stain the cell down deep. And then when you're washing out one of the stains of the Gram stain, it'll be harder to wash out the cell on the bottom of the cells because it has to wash out of that cell, and then the dye will go into the next cell, etc. So that's why we want a bacterial smear that's very thin. And let me reiterate, when you make the bacterial smear, that is not part of the Gram stain. It is not a part of staining when you're making the bacterial smear. It's something you do before you do the stain. You then allow that bacterial smear to air dry and then heat fix it, gently heat it. We'll talk more about that in our next lesson, which I guess will be next week. And then after that's done, you can then begin the staining procedure for the Gram stain. First, we flood the slide with crystal violet, and you leave it on for 1 minute. You then dump it off and wash the slide in cold water, removing the worst of the water. You then flood the slide with iodine. Iodine is a mordant, and you apply that for only 1 minute. You dump the iodine off, wash it again gently in cold water, get the worst of the water off, and then you flood the slide with the decolorizing agent, which is oftentimes acetone and ethanol, but it doesn't have to be this. It could be another decolorizing agent. Usually if it's different, it's acid and ethanol, which works the same as acetone and ethanol. You can also have simply 95% ethanol. That works similar, but it doesn't work as quickly as acetone and ethanol. And so you have to decolorize longer when you're using 95% alcohol. Then when you're done with that, you quickly, immediately wash the decolorizing agent off of the slide, then dump the water off, and then flood the cell with safranin. Safranin is called the counter stain because it's a second stain that stains differently than the primary stain, the crystal violet. And you stain that for 1 to 2 minutes. You only need 1 minute as long as the safranin is strong enough. If the safranin is very weak, you may need to apply it for 2 minutes. Yep, don't want to do that. You then dump the safranin off and then wash the slide gently with cold water. And then you dump that water off and then you blot it dry. Blotting it dry means that you get the slide and you put it between some bibulus paper. Let me go, this has the slide and this is the bibulus paper. The bibulus paper will be attached to a pad of paper. Let me get a pad. What you want to do is rip off a pad of the bibulus paper, and it's very thick paper, and then fold it, and then put your slide, I don't know if you can see that, fold it, and then put your slide in the folded bibulus paper, and then you can gently press down, blot it. You do not want to wipe the slide against the bibulus paper like that. You just want to blot it down. And then you'll remove enough of the water that you can actually use the slide under the microscope, even if you use oil. Any question about any of that? All right. When we're going through the Gram stain, you first apply crystal violet, and all the cells will take up the crystal violet, the Gram negative and the Gram positive, so they'll all be blue purple in color. We then apply the mordant, and the mordant will bind to the crystal violet and intensify the stain of the crystal violet. The iodine crystal violet complex is larger than the the crystal violet alone, and so it will intensify the stain of the crystal violet. The cells will have a little darker color because it'll show up better because there's a larger molecule that's now colored. The crystal violet is bound to the iodine. That's a little larger than the crystal violet. And it will change the color slightly. Instead of a blue purple, it'll be a purple color. And you can see that there's essentially no change in color. It's a very slight change. You then apply the decolorizing agent, and that will pull the crystal violet out of the Gram negative cells, but it will not pull the crystal violet out of the Gram positive cells. So the Gram positive cells will remain purple in color. The Gram negative cells will be clear because the crystal violet iodine complex has been pulled out of it. You then apply the safranin, and the safranin will get in the cells and will stain the Gram negative cells a pinkish color. The Gram positive cells will retain the purplish color. Any question about any of that? All right, you do need to know this slide for both the lab and the quizzes, what the color is of the cells at different steps in the Gram stain. Any question about any of that? All right, if not, I'm going to stop the lecture a little early, and then we will come back to this and talk further about the gram stain next week. Any question? All right, if there's no questions, I will see you at 6:30 for the lab. Bye.